and we found 10 hertz, the frequency to be 10 hertz because it's velocity over the wavelength. And then we found the angular frequency, and it's 2 pi times the frequency. So here we put 2 pi times the frequency we found up there, and we found it to be 20 pi. Once you find that, then k, the wave number, is 2 pi over the wavelength, and so you calculate it to be pi. Once we have all of that, now we're ready to construct our equation. To y equals a amplitude cosine k times x minus, since this is in the positive direction, angular velocity times time. And then we just plugged in all our numbers. Amplitude, the pi is the wave number, x minus 20 pi is the angular frequency times time. And then now we're ready to solve it at x equals 0 and time equals 2 seconds. So you just have to plug in, and this whole thing, when you plug it in, equals cosine of, it's just 1. And then 1 times 0.1 is 0.1, so the displacement that y is 0.1 meters.
Thank you.
You see any problems with that at all, or does it make sense? It's actually pretty similar to a problem that I was coming up with, so yeah. So yeah. Good. I'll take this. Okay, Cody. Yeah, that one okay. How about you? Oh, you would pick this up. Your guy in this group. Why is this so tilted?
We have a cart with a mass of 20 grams that is pushed back upon a spring. The spring is compressed from a half a meter to 0.15 meters. The spring constant is 30 newtons per meter. What is the velocity of the cart when it is released? So we drew our picture, and then we have potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. The kinetic energy initially would be 0, and the potential energy in the final would be 0. So then we just solve that for velocity.
Okay, does that make sense? So that's kind of a Hooke's law problem.
Right.
Yep. All right, thank you. Next group. You're good. Involving Superman.
Really? You gotta wait and see, don't you, Dave?
Of course it will. It's just their trademark. Good.
Yeah. Brainiac plans to unplug the town dam in hopes of flooding the town with water. The town in question is Metropolis. The water level is 154 meters high. Superman must save the town from flooding by welding a metal sheet over the hole with his laser vision. What pressure does Superman have to withstand in order to patch the hole? So this is one of those Bernoulli's equation problems. At the beginning, the velocity is 0 because it's just at the top there. And it's also 0 at the end because he's holding it. So those both cancel and you end up with all this, and then we just plug in numbers to find our answer.
I'm having a hard time picturing it. So is he on the reservoir side of the water?
Yeah, he's holding.
That's like your water level.
Okay.
And then you got like it going on like this. So then he's gonna like
Oh, he won't
patch
patch
it
over
up
there.
right there.
Okay. Okay, and and then, yeah, he has to stop at the, I got you.
So we just assume that B1 is 0. I
Yeah.
guess B2 is 0 too.
It's studying though. What about the project? Are they both 18?
But it's all Pascal.
Oh, yeah, you
Pascal.
were talking
The first one is all right.
Another one of those equations. Except we have the pipe. It starts out wider and then it gets skinnier. You know, the initial pressure and velocity, and then this is height at 0. And then you want to find the pressure on this side, knowing the velocity and the height. And then you have density of water and gravity to be given.
And then do you have the velocity changed up too?
The what?
The velocity.
Oh,
Gives V1 and
okay.
Oh yeah, these are two different.
And then you just rearrange to get P2 by itself and then 7.
And just out of curiosity, would those size of the pipes be the same?
No.
Yeah, because the B came, so you need
Yeah.
the size of the pipe. Okay, that's not part of the problem. All right, good. Makes sense to everyone? All right.
Mine's pretty much the same as the last groups. Like, exactly.
Except it's, no, yours is opposite.
Going down.
Right. And we're trying to find the pressure at the end of the pipe.
Okay,
So, another Bernoulli's equation.
okay.
Do you want me to go?
Is the pipe the same size the whole way, or?
Yes, same size. Thanks to the original.
Well, it can't be the same
Yeah.
size. as your
Or no,
piece
not the
cake.
same size.
Yeah.
Yeah. So it would be smaller.
Yeah, the velocity is changing from 10 to 15. So.
Yeah, so the pipe narrowed, but
Yeah.
that's okay. All right, thank you. Makes sense?
Yeah.
Do an equation where just the solve the velocity of the second one is the back pressure.
Oh, yeah, we can do that. That sounds like a pretty good one, actually, having a pipe that narrows.
Giving me
Brittany?
idea.
Okay, you count 17 complete waves past a certain point in 120 seconds, and you measure 5.5 meters from a crest to a trough on the passing waves. What is the velocity of these waves? So these are the equations we're using, and yeah, you just, for the frequency, you put 17 waves over 120 seconds, and then for the wavelength, you have to multiply 5.5 by 2, or whatever, as you see. And then velocity, frequency times wavelength, and yeah.
What's the two?
This two,
How do you get the wavelength?
Yeah, because it wasn't.
5.5.
5.5.
I got you. Yeah, see, when you said from crest to trough, I thought it was the amplitude.
Yeah, that's why I drew the picture.
Okay, I got it.
Rather
That'd
than
be half.
amplitude, 2.7.
Yeah.
All right. Pearl and Marcus, you went, did you go on? Yeah, that's no problem. Then, one
find some venues for new
So these are a popular problem.
That was a good pipe.
It's just the same size of pipe, it's just they use that one in 2 meters and then gas for the velocity at the end.
Yeah.
Everyone was in pressure.
Okay. Then the pipe would have to change its size to accommodate that.
Yeah.
Or, maybe not fill up anymore or something like that fully. So, all right, makes sense. Spencer.
Yeah.
Do you leave your?
Yeah, we do.
I just did the pipe narrowing. So, you have the radius of the first pipe size, and then you have the radius of the second pipe size, so you have to find the area using pi r squared.
Oh, what's the problem?
Yeah, this is circle not. What?
So you have a pipe with a water, or with a fluid progressing through it at velocity 1, and it comes out the other end of a pipe that's narrower.
And what's velocity 2?
Yeah.
Okay.
So, yeah.
Mechanical question mark.
Oh, I got you. That's, okay, the problem's there.
Yeah.
So is this like the A1, B1?
Yeah. That's,
Okay. Okay.
Anyway, so yeah, you have to find the actual area using the radiuses that you were given, and then solve for V2. It comes out like way faster than I thought it was
It's a
going
half-meter pipe with water traveling at almost the speed of sound. That's pretty serious.
That's not this speed. That's actually how they cut like McDonald's French fries. They have a giant water cannon with a grater in the end.
I think I've seen pictures of it.
Yeah, no, it's modern marbles now. That's cool.
I've seen that, yeah. Try to make it all nice and even. You
Alright, so we did an intensity of light problem. Yeah. So you turn on a 60-watt bulb at a distance of 2 meters away. What is the intensity of the light? And then part B is you step a meter closer. What is it then? So you have to know intensity is power over area. So to find the area of the circle around it, you have to do the 4 pi meters squared. So you just do that for 2 meters, and then put it on the bottom of the 60 watts. And then you do it again for B. You step closer.
So you found it a factor of 4 big spread. Good. I like that problem.
You have the distance is quadruple.
What else up the cycle?
4 pi out of
Yeah, in that area.
We did another pipe work. So goldfish died and gets flushed down the toilet. The pipe goes down 10 meters and makes a turn and continues horizontally. If the pressure in the pipe is 1.001 times 10 to the 5th pascals, and the goldfish starts at rest, what's the velocity? 0.2, which is that.
Okay.
Given the density of water, it's just.
So what do you do?
Well, the initial velocity is 0, and then the final height is 0.
And then you took the pressure to be the same.
No, pressure 1 is atmospheric pressure,
Okay.
and then pressure 2 is, is the pressure of the pipe.
Oh, okay, I got you.
Yeah. You just solve for velocity.
make sense to you, to everyone? Yeah. Oh,
So we have one.
okay.
We did the high jog lift problem.
Okay.
So high jog lift consists of an incompressible fluid inside two connected arms, form a U shape, and the cross-sectional radius of side one is 20 centimeters. And it's 1,050 Newton force applied to that side. And side two has a 21 centimeter radius. So we found, and we're trying to find what force will be applied to side two. So we just have to find our area of our two sides, and then change in pressure one is equal to change in pressure two. Pressure is equal to force times area, so you set those equal to each other. And then you solve for F2. So we have F1 over F1 times area 2 over area 1 is equal to our. But I didn't get that part down.
Would you have like a blue force?
Well, this one would be the hydrology where you have the pressure. The pressure, if you change the fluid pressure by exerting a force on one side, that pressure gets transmitted everywhere, including over the bigger area on the other side, and a different area on the other side.
Oh, okay.
And so you can change forces that way by having different areas.
So you're changing force on the second.
All right. Leave that up here.
Pulsing comes in the distance. And then 80 because this 80, yeah, you're
Can we put that behind you and even it up a little bit if possible? Okay. All right, so I noticed that there's a lot of Bernoulli problem ones on those, so I won't worry about that too much. Those are good problems, and but maybe some wave problems would be nice to go over, and also some simple harmonic motion.
Yeah.
So we'll do one simple harmonic motion. So remember what our topics are. Simple harmonic motion, waves, and the fluids. And I'll just list really quickly. Kind of the subtopics.
So is wave, spring, is that included in simple harmonic motion? Okay.
Yeah. So under simple harmonic motion, we had Hooke's law. We had the simple harmonic mass on a spring. Mass oscillating on a spring. And in this one, the angular frequency was square root of k over m, where k was the spring constant. And then we also had the pendulum at the end, which for small angles behaves like simple harmonic motion, and omega was square root of v over the length of the pendulum. Okay. 2 for waves. We talked about the relation between velocity, what is a wave first of all, but velocity, the relation between velocity, frequency, and wavelength. Then equation for a wave is a cosine of 2 pi over the wavelength x minus 2 pi over the period t. Or, sine, could be sine 2. Plus or minus, depending on the direction of travel of the wave. And we talked, and this A was the amplitude of the wave. And then finally we talked about intensity of the wave. Power transported in intensity. Okay. And then 3 were the fluids. So we first talked about density. Then pressure. And using this, we looked at hydraulics. See, after we did density and pressure, we did hydraulics and also pressure to get a depth. Hydraulics, pressure at depth. Then we did buoyancy. And then finally we did the flow of the pipe and various applications of Bernoulli's equation. And at the end we also did very, very quickly continuity equation. What it's called. And this would apply to a filled up pipe. And so what I think by the way, you can pick it up after class or whenever you want. I think we'll talk about some of this really quick, and also the waves, maybe the intensity and power of waves. I like that. Okay, so let me give you a couple of problems. Remind myself what these are. Okay, so the first problem I'd like to do is a Hooke's Law problem. So imagine I have a spring, and then I put a 10 kilogram mass on there, and then I started it oscillating. So I pulled it back from its equilibrium position by an amount of 0.5 meters. Then I let it go. And then this thing oscillates back and forth. So this is where I pulled it back. Let's say that the frequency of motion is 0.5 hertz. So my question is 1. What is K? 2. How much energy was in the spring, or how much energy in the system? 3. How fast was the mass going when it goes to its equilibrium point? makes sense how to, what these ones are. So how would you first of all, and we can, yeah, I think we have time to do this one. So how would you get K?
Force of spring equals K times D, right? This.
That's true, but did I give you any of that?
No.
Oh yeah. But isn't the force gonna be mg or no?
Well, that would be happen if it was, this is horizontal, so.
So it can't.
Yeah. By the way, this is frictionless, so probably ought to mention this frictionless.
How can you find the angular frequency and then find it that way?
Yeah, that's right. That's a good way to approach it, right? If you know the angular frequency, the omega, and you know a mass, you'll automatically know what the spring constant is.
Mm-hmm.
So that's one where thinking about that. You know, if this is all you're given, frequency is all you're given, you know of mass, you know, the clue immediately is frequency is this. What's that mean about angular frequency?
So 2 pi over 6
So-
So on this one, the frequency F is 2 pi times omega.
Mm-hmm.
And omega we know for simple harmonic motion mass on a spring is K over M. So you can, and you know M, you can get what K is.
Mm-hmm.
Okay. Now, how about how much energy is stored in the system?
So like there's potential energy at the end and then kinetic energy in the middle, right?
Yeah.
So potential energy initial equals, well, potential and kinetic energy initial equals kinetic energy final.
That's right. At any point, the total energy is the same.
Mm-hmm.
So potential plus kinetic equals total energy.
That's right. You know what K is now.
Mm-hmm.
You know how far you pulled it back.
Mm-hmm.
It wasn't moving when you pulled it back, so there's no kinetic energy when you let it go. So what would I do? Yeah, I'll call this. Okay, so I do. What's the energy stored in the spring?
So
1/2 d squared.
That's right.
because
So if
that's
I pull the spring back from its equilibrium position at distance d, the energy stored in it would be 1/2 kd squared. And so when I pull it back all the way, that's how much energy it had, because there wasn't any kinetic energy at that point.
So that's all we need to do.
Yep. 3. How fast is it moving through equilibrium?
Now we have to do 1/2 mv squared.
So initially, when I pull it back all the way, here, there's no kinetic energy, and the total energy is 1/2 kd squared. When it's going through equilibrium, it's not stretched from its equilibrium position at any point. So all its energy is kinetic energy now.
So that's going to equal?
Okay. And you
So
can get
that's
the B from that.
Okay.
Does that make sense?
potential energy equals kinetic energy.
So that's the type of problem for simple harmonic motion that I kind of like. So. It's not complicated mathematically, but you have to think physically.
You have to know this, right?
And about it. So there's some problems in there about it. There's probably some other problems you can get online if you need. You can do this type of thing. Waves. Let's go ahead and do this one. So probably you know, we did a lot of examples with various light waves and stuff. The reason we did examples with that is we know the speed of that wave, of light waves. Let's say I use a different type of wave, like a sound wave or something like that. Let's say V is equal to 300 meters per second. All right. Let's say that sound is created by some frequency of 1,000 hertz. So my question is now, what is lambda for the wave? That's first part. Oh, by the way, I'm going to erase this fluid thing. So, sorry. I don't have any room. B. If amplitude of the wave is 2 centimeters, so that's actually a huge sound wave, but that's okay. I mean, that's the vibration of the molecule being 2 centimeters. And the wave travels in plus x direction. What is the distance from equilibrium, you know, distance from equilibrium of the material that the wave is traveling through? At t equals 1 second, x is equal to 10 meters. Oh, let's do 0.1 second. I can't do it in the actual terms of that. Okay, sorry.
What is the distance?
Can you read through that one more time?
Okay, if the amplitude is 2 centimeters and wave travels in the plus x direction, what is the distance from equilibrium of the material the wave is traveling through at time t equals 0.1 seconds, x equals 10 meters? We'll assume a form where it's using this form of the wave.
But if you did like for that formula, if you did like what I did earlier, the wave number times x minus, that would be fine. Okay.
Yeah, 2 pi over lambda, this is the wave number.
Yeah.
Yep.
Okay.
Distance.
Good?
What would we be solving for? Yeah, what are we solving?
The y.
It's the y. Oh, y.
So this is actually a formula for the distance displacement from equilibrium at a given point on the wave. So that's what you would use. This is the displacement from equilibrium at some point on the wave.
And lambda is what we solved for in the beginning of it.
Yeah.
Right? A for A.
So.
And we're subtracting.
And in C, suppose the wave was outputted by some sort of spherical speaker, so it comes out all in a sphere. Suppose wave from point source. This means that it's spherical, as a sphere in all directions. Power of the source velocity at 3 meters.
Do they make speakers that do that? Go
No,
which direction?
it's just easier this way.
Fair enough. I was just curious.
Well, you know, they do have things that are that way, like a gunshot, for instance, is basically
Yeah.
the same in all directions.
Yeah.
You're the same in all directions.
An explosion.
Explosion.
Basically, any type of percussive noise is gonna
Yeah.
originate from a point.
Yeah, exactly. So this would be just fine for that. So what is intensity? 3 meters from the source.
So would we use the 3 meters as a radius or diameter? Radius.
Radius,
Okay.
yeah.
We're just making sure.
For drawing a picture very much helps. All right, so these are kind of, I guess I'll focus on those. The fluids are more recent, so let's do this one. How would you get the wavelength?
Oh, you just time, divide velocity divided by frequency.
Frequency over velocity.
All right, the only thing I remember is that velocity
Equals
is lambda times f.
Yeah, so
Yeah. And so if I know the velocity and I know the frequency and I want lambda, I solve for it. So v over f. Make sense?
yeah.
So that would be the 300 meters per second divided by 1,000 hertz. So that would be 0.3 meters. B is the amplitude is 2 blah 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 here. Sorry. I didn't have to read it all. I want to use this equation. This is the equation for the displacement from equilibrium of a point on the wave. So the amplitude is 2 centimeters. So I do displacement. Maybe just dy. You can do y. I don't care. Is equal to a 0.2 centimeters. Is a cosine of 2 pi over this 0.3 meters times x equals 10 meters.
Wait, don't our centimeters and meters have to be all the same units?
Well, as long as these two are the same, but yes, I could put these to meters.
Which two?
The 10 meters and the 0.3 meters.
0.3 meters, because those guys are, okay.
Yeah.
Okay. So we're
Everything
solving
inside
for
the
y.
cosine has to end up being dimensionless. You can't take the cosine of a meter. It doesn't make any sense. So you have to have all the units cancel out in there. Okay, minus, because it's traveling to the right, the plus x direction, 2 pi over the period, which was the frequency, 1 over the frequency, so 1,000 times t, so that's 0.1. Anyway, you'd have to evaluate all of this. So 2 pi times, this would be end up being 100. This would be 2 pi 10 divided by 0.3.
What did you get for the big T?
That's 1 over frequency.
1
Yeah,
over
so
frequency.
T.
Okay.
1 over f. So
Okay.
1
So it
over
would
t
be,
is f.
okay.
Yes, okay.
Yeah.
So 2 pi, or 2 centimeters. Cosine. 2 pi over 0.3 meters.
Oh, so it's 2 times that.
Times 10 meters. Minus.
Because it's,
traveling
T is 1 over
plus
that.
x direction. 2 pi times 1,000 hertz. Okay, that's 1 over 3.
Okay. So,
Times 0.1 seconds.
those always look to me like those freaking fractions. Can we take pictures of the?
Oh, yeah, if you want to take them in. So you guys got your spots.
What?
You want to go ahead and take pictures.
I'm not in my car. My phone is acting like whenever I plug it into an outlet, like especially weird. I thought it was the first time I was going to charge it. Yeah. But I had
I know, it's that long.
Let's say for probably 17. I just assume in my mind if I wanted to.
They landed.
Yeah.
Hey, Samantha.
It's for the base one. The base one's 32. It's like $600. That's insane. The lease on the gig is $800. Which is hilarious though, because if you think about it, the first iPhone came out, like the first iPhone, the highest rating was like $800, which is crazy now because
I
like,
just
an
always
iPhone 5
get
you
confused
can
with
get
between
the
circle
lowest gig.
Okay. No, I mean like whenever we do the Bernoulli's equations, these are all circles. Yeah, but then this is zero.
Okay, yeah.
Area.
That seems pretty easy.
I'm gonna have to study that.
All it is massive repulsion. That's what density is.
I know, I need to go over all the.
Yeah, I was scared about this, but now I'm not.
Well, you just gotta.
I know they use this. Basically, it's showing the water up.
No, I'm just, I don't have my phone.
Memorizing it.
If I had a photograph degree, I don't know how much laser, I don't know how much laser I can get, okay? Like, let's be honest.
Photographing the
How about-
flipping through the book and then just throw it
Well,
out.
it's like what we did before.
Never actually met.
Yeah, you'll have to come by. It's hard for me
I've
to
seen, I've watched videos of people who do like those memory competitions where they have to memorize like, they take like 4 decks and
Oh, yeah. We got another 2 minutes.
It's insane. Can you send this? I appreciate that. Sorry, Jacob, I've done it.
No, you're good.
Oh,
absolutely. Not good enough.
Yeah, it'll be a lot more intense.
Just cracks. I couldn't find an answer, so I
Okay, So let's go. Okay, I didn't need all these. Yeah, we'll be done. Of course, I'm not sympathetic to the chemistry people because they took forever. I was trying to get into a class.
I feel
But then I'm